Swayam Prabha. Digital India. Educated India.
So we can begin the session. I think yesterday you've already had a couple of lectures on blockchains. So can you tell me some of the concepts you studied yesterday? Anything that you learned? Yeah, in blockchains.
The blocks, the header, the format.
The format of Bitcoin. Okay, good. So you're probably experts on Bitcoin, right? Which is making the news almost every day, right? And there's a lot of controversy about it. And nobody knows who the founder is either, right? Which makes it more exciting, right? Who is this genius who came up with this idea and wants to remain in the background, right? So what is the problem really that proof of work is trying to solve? So we'll just have a slight recap of proof of work. And the problem here we are trying to solve is something called consensus. So suppose we have a blockchain. This is the genesis block. And as you know, each block has a hash of the previous one. And given that we have a certain number of blocks in the blockchain, we want to know what should be the next block. So everybody participating in this network, let's say that there are various participants. They want to all agree on what's going to be the next block. Right? And that's what we mean by consensus. Now, Bitcoin is a Bitcoin blockchain essentially is considered a type of permissionless blockchain. So have you heard this term? Was it discussed? Permissionless versus permission. So what was the old scheme of things? So before Satoshi came onto the scene, normally when we talked about consensus, you had a certain number of participants, some n people, and they wanted to have consensus about something, right? And so this n was a fixed number. Okay, so this is, I'm talking about the earlier scheme before Satoshi. So n was fixed, you had some n number of participants, and how they achieved consensus was typically that somebody was the leader and he would, let's say, propose the next item to go into this list. Okay, something like, we can think of a blockchain. Of course, blockchains weren't there then, but you can think of adding to some database, some information gets added every so often. So there was a leader, and this leader would propose what is going to be there, let's say in the next block. Okay? So it was straightforward enough, but the question is, what happens if the leader fails, for example? Then you need to re-elect a new leader, right? Or what if the leader misbehaves? What if he proposes 2 blocks instead of just 1, right? So then he has to be evicted. And so they have to have some protocol, these n participants have to have this protocol to change the leader if required, or somehow they all have to say that we have to agree on the block which has been proposed. Right? So that was the idea around there, and essentially it used some sort of a voting mechanism. So each of these n members had, let's say, one vote, and they could cast that vote in the protocol. It could be a vote saying that I accept the block proposed, or it could be a vote saying that I want to get rid of this leader because it's misbehaving. Okay? So it was voting based, and there were lots of protocols designed. So one of them is called Raft, which can handle a leader failure. Okay, but there are other protocols like Byzantine fault tolerant protocols, something called practical Byzantine fault tolerant protocol, which can handle even a leader who misbehaves. He might propose multiple blocks or do some mischief, and those protocols can get rid of these mischievous leaders and elect new leaders. Right? So that was sort of the state of the art before Satoshi came onto the scene. Now what Satoshi wanted is to have some sort of a system where the number of participants could be anything. There was no fixed n. So what is this permissionless blockchain? So n can be anything, any number, and it can even change over time. Okay. So what Satoshi wanted is some sort of a payment system which is not controlled by a central entity. There is no bank controlling it, or nothing like the Reserve Bank or anything like that, no trusted entity. He wanted to have some sort of a peer-to-peer system where anybody in the world could join, anybody could become a participant, and still you could have a working system that you should be able to handle situations where if a leader of a block is proposing something wrong, you could get rid of him, let's say, or you could discard his block, right? And so the same functionality that you would have in the older systems, but in a permissionless system, right, where anybody, you or I, could even join the network and participate and decide on what's going to be in the next block. Okay? And people thought this problem was impossible to solve. Okay, so actually the computer science community thought it cannot be done. And why? If you think about it, so you have these various participants, and we said earlier that they have to vote. So how are we going to do voting over here in a permissionless system? Because after all, anybody can join. There could be 1 million people, 1 billion people, and so on. I mean, it could be in the worst case, right, into billions. And how do you define who is a person over here, right? So in the earlier systems, you had, like, let's say, n machines, and each machine would be, let's say, have a particular cryptographic key, and using that key it would cast some sort of a vote, right? And here in this system you could have any number of people. How are you going to decide who has power to vote, and how do you decide who is an individual, right? So one way to do it is you say that you have IP addresses for each machine, right, and corresponding to each IP address you have one vote. Okay? But suppose I want more than one vote, then what would I do? I could just join the network with multiple machines with multiple IP addresses and then cast more votes. Right? So nobody knows my identity because this is a permissionless system. People are joining from anywhere in the world. Right? So how do you decide, how do you sort of ensure, let's say, that one person has one vote? And that was an issue that people thought cannot be solved. And the problem over there is called a Sybil attack. So a Sybil attack is one in which somebody can create multiple identities. Okay, so if I am an attacker, I will want to cast more votes so that I have more control over the system, right? And if I get, let's say, a large enough number of votes, then I could play a lot of mischief. Maybe I could push out somebody else's transactions, or I could put in some fake transactions in the blockchain, right? So this, people thought it's impossible to solve this sort of a problem. Another issue was that the earlier protocols like Raft and PBFT and so on could only handle a few tens of nodes. So n could be of the order of 10 or few tens, right? And the protocol wouldn't scale up when you had very large number of participants. But in a permissionless system, you could have potentially thousands or even millions of participants. Right? So people thought it was an impossible problem to solve. And what Satoshi did to solve the problem, it turned out that he came up with a very simple solution called proof of work, which you've already looked at yesterday. And what he said is that people create a block. So this is the block header. And you're familiar with the structure of the block, right? You have a Merkle tree. And at the bottom, you have a set of transactions. So this is the Merkle root. So what he said is you have a hash to the previous block. You have this Merkle root, and you have a few other items in this particular header. You have, let's say, a timestamp. And then you have this thing called a nonce, right? Right, and so how do you, so how does the proof of work protocol work? So how do we proceed with this? So somebody wants to create a block. So what does he have to do? Anybody? Yeah. Yeah. So it's actually very simple, very straightforward. So what Satoshi says is you have to find the hash of this block header. I'll just and you have to find a hash which is less than some threshold. Right, and this threshold is decided by the protocol. Right, and it's actually a very simple protocol, but it's very subtle, and we'd have to think why it even works. Right. So how do you do this? Because this hash function is something like unpredictable, right? If I tell you what the contents of the block header are, it's very hard to predict what the hash is unless you actually evaluate the hash value, right? You have to send this hash, this block header through the hash function, right? So you send the header through the hash function, and you get the hash value. Okay. And let's say you do that and you find out that the block header has a hash value which is, let's say, larger than the threshold. So what do you do then? So what you have to do is you have to keep trying to change this nonce value multiple times till you actually solve the problem. Okay, so this is the problem that we are trying to solve. So what we do is, suppose I am a Bitcoin miner, I create a block looking like this, I choose my transactions, and then I keep replacing this nonce value multiple times. Could be millions of times, billions of times. And if I am able to find a nonce value so that the output of this hash function, the hash value is less than the threshold, okay, then I am successful. Right? So somebody who creates a valid block, okay, is going to of course have a nonce value such that this problem is solved, and then he broadcasts the block and then it's added at the end of the chain, right, and then the game for the next block begins. Right, a very subtle, a very simple sort of solution which is much simpler than the earlier protocols that existed like PBFT and Raft. Right. So, why is this working? I mean, so how has he solved the Sybil problem? Okay, so any ideas? So we said earlier there was a Sybil problem in a permissionless system that somebody could try to cheat and pretend to have multiple identities. And since there were no names or anything like that, there was no trusted authority to say who is who. An attacker could say that he's 10 persons or 1,000,000 persons and he would get so much more voting power, right? And he could mess up the protocol. So here, how has Satoshi solved the Sybil problem? Pardon me? He has to solve this problem. So there are no explicit votes as such in Satoshi's protocol, right? You don't have people voting and counting number of votes and things like that. He's sort of done that voting in the background. And what Satoshi says is that I can't really count number of people, I cannot tell who is who, but I can tell how much computing power you have. So Satoshi's idea, and if you read his original white paper, which is actually quite easy to read and you'd find it on the internet, he says that one CPU is equal to one vote. That was his idea. Okay. So you can use a CPU. Of course, nowadays they use specialized hardware to solve this problem, right, this hashing problem. So Satoshi said that I can't identify you, but I can tell how much computing power you have. So if you have one CPU, it may take you, let's say, 10 hours to solve this problem, right? But if you have 10 CPUs, it may take you 1 hour, right, or 1/10 of the original time, right? So he said that if you want to have more power or more voting power in the system, you buy more CPUs. And you cannot pretend that you have more CPUs than you have, because you actually have to solve this computation problem. Okay. So that was his insight. So he says, I'm not going to look at persons, number of persons, I'm going to look at CPU power, and through this computational problem I'm going to ensure that you cannot fake your CPU power. Okay, because of course you might be lucky sometimes, but on average the probability of your solving the problem before anybody else really depends on your CPU power. The more CPUs you invest into doing this Bitcoin mining, it's called the Bitcoin mining problem, the higher the chances of your winning the game, right? So this was a very clever solution which solves the Sybil problem, right? And probably one of the big inventions, I would say, of the early 21st century. Right? So what were some issues with this proof of work? And one of the issues that people say is the power consumed. There's a huge amount of power consumed by Bitcoin. In fact, just solving this Bitcoin mining problem uses more power than some countries, right, smaller countries. Okay, so a huge amount of power is expended into mining these blocks. Okay. So this is one problem. With proof of work. Okay, so there are also other issues in that you cannot generate these blocks very fast. And why is that? So this is the genesis block, and this is my block chain. Right? So suppose we have a chain up to this block shown over here, and suppose I set my threshold very high. So remember that I want my hash of the header to be less than a threshold. If I want these blocks to be generated faster, I will just set a larger threshold. Right? So instead of blocks coming once every 10 minutes, I could get them once every minute or so, right? Just by changing this header. Now, who are these people generating these blocks? So they are participants anywhere in the internet. It could be you or me. Right? You can start on your laptop, you can create a Bitcoin node and start mining Bitcoins. Right? And so essentially you would be trying to solve this problem. Right? So if you have the threshold very large, that means you have a very easy problem to solve. You could have many people, let's say A and B, generating blocks at more or less the same time. Right? And in which case you will not have a single block pointing to the previous one. You could have a situation like this where you have a fork. And this is a problem because we want only a single blockchain, right? Because these blockchains have a list of transactions, and everything has to be consistent with everything else already there in the blockchain, right? If you have a situation like this, somebody could pay money in A's block to one person, and he could use the same money, let's say, to pay another person in block B, right? And that's not fair. You should be able to spend your money only once, right? So we want a single chain which records all the transactions of Bitcoin, and these sorts of forks are not good. So suppose a fork occurs. What was Satoshi's solution to solve these forks? How to decide on a single chain after this?
More the number of blocks.
Yeah, so in this situation right now, what I've shown, the two chains are of same length. So what the different miners do is they try to mine on one of these blocks. They choose one of them depending on which one they saw earlier, right? And what will happen is that one of these, let's say somebody wins the game and he creates a block on A's block. Now this chain becomes longer and everybody says we are going to follow this chain. Okay, so this is his fork resolution solution, right? But ideally you don't want these forks to occur because there's uncertainty in the system. People don't know which block to accept, right? And so you want to reduce the number of forks. So in this particular system you have the threshold typically quite small, so that it's very unlikely that two people at the same time are going to generate a block, right? So Satoshi has, or I should say Bitcoin has one block per 10 minutes on average, right? So sometimes blocks might get generated faster, but on average a block is generated every 10 minutes. And each block has, let's say, a few thousand transactions. So roughly we get something like 7 transactions per second, right? This is what we have in Bitcoin, and this is really not good enough for a global payment system. You want at least thousands or tens of thousands of transactions per second, right? Right now many of you have used UPI, right? Whether you're using PhonePe or Paytm or Google Pay and so on. So there you would want the system to support tens of thousands of transactions per second, right? Because so many people around the country are making transactions all the time. So 7 transactions per second is really not good enough, right? So of course, if you're using something like proof of work, you're really stuck with something like this, because if you want to have blocks with transactions generated faster and faster, you would have to increase this threshold and then you'd have more forks. Okay, and if you reduce the threshold to get rid of forks, then you're left with 7 transactions or 10 transactions per second. Okay? So people were thinking how to get around these problems. right? And they were thinking in the context of permissionless systems like Bitcoin, where anybody could join and participate in the system at any time. So this brings us to proof of stake. So it's another idea out there, and proof of stake is used by the current latest version of Ethereum. Just recently, Ethereum shifted to proof of stake, but there are other blockchains like Algorand, which also are stake based, and several others, right? So they are all worried about energy, using too much energy for maintaining a blockchain. So they want to come up with some other scheme, right? So proof of work says one CPU is equal to one vote, and it works well because it doesn't consider any sort of identity of people which could be faked, right? And people are wondering, is there some other resource which we can use for voting which cannot be faked? So do you have any idea? So you don't have to think in terms of proof of stake or anything like that. I mean, even if you know what it is, but is there some resource that we can use to do voting? So suppose somebody can either directly or indirectly prove that he has a certain amount of resource of some kind, then he gets that much proportional vote, right? And that's the idea that people were thinking about. And Satoshi came up with this idea which looks at CPUs. So he says, you solve this puzzle and that will prove to me that you have a certain amount of computational power and you get that much voting power, right? The more CPUs you have, the more likely it is that you will generate a block. So what kind of resource can we use instead of, let's say, CPUs? So what other resources do computers have, let's say, right? So that would be sort of an ideal thing to look at, because you have a machine. So besides CPU, what other resources does a machine have? Pardon me? Memory, right? So one answer is memory. So that's a good answer, and people thought about this too, right? And so they said that I can give you maybe a computational problem which requires a lot of memory, maybe not so much of CPU, but if you can solve that problem, then it proves that you have this much memory, right? And you use that in order to mine blocks. Okay, that was an idea that people thought of, but of course then you have to spend a lot of money in buying memory, right? So again, there's a lot of money to be spent over there. Of course, you're not burning up a lot of energy by doing a lot of hashes, okay? And of course, you would still have to solve some problems, so that would use up some amount of energy, okay? So memory, anything else, right? So anyway, this was what people were thinking of, and so we are still thinking about the real world, some sort of a physical resource.
You can consider the amount of time that node has been in the network.
So could you repeat?
You can consider the amount of time that the node has been in the network, something like that.
Okay, so the one idea is the time for which a participant has been in the network, and yes, the thing is, how would you prove that you've been around for long, right? Because there are no identities as such. Yes, and then you would be giving an unfair advantage to somebody who's been around longer. Yes, so that there would be less incentive for people to join now, because, right? Yeah, so those are clever ideas, and you never know which one is going to hit and actually make it, right? So it's good to have a lot of these ideas, throw them up and discuss them with people. That's how research works, by the way. It's not that the first idea you think of actually becomes big, right? Maybe out of 10 ideas, one idea might really succeed, right? So this is that's an interesting idea, and people have thought along those lines to some sort of proof of elapsed time, and people, all sorts of things, and sometimes people think of using specialized hardware in order to solve some problems, so that I mean all sorts of clever ideas. But people were earlier thinking about a physical resource which people cannot pretend that they have. They actually have to prove that they have it. But what other resources do people have? So what about looking at the Bitcoin itself? So if you look at these blocks, of course I am combining the header and the transactions, everything into one. So the block has transactions, and essentially these transactions are paying from one account to the other, right? That's the most basic type of transaction you have. So various people already own Bitcoin, and they cannot fake how much Bitcoin that they have. Everybody can see the blockchain, it's a public blockchain. And if somebody has 10 Bitcoin, let's say, he cannot pretend that he has 20, right? Because he has the keys only for those 10 Bitcoin, right? Or somebody else has, let's say, 100 Bitcoins, right? He cannot pretend to say that he has 1,000, right? So you cannot fake how much Bitcoin you have. So people said, why not use this resource in order to do consensus? Use the amount of coins that somebody has on a blockchain. Of course, Bitcoin doesn't yet use this idea, but if you think of Ethereum, you have the Ether coin, right? So you cannot fake how much Ether you have. So people said, let's use this as a resource in order to perform consensus. Okay. So since everybody anyway knows how they agree that which keys own how much Bitcoin or Ether or whatever, let's use that as our physical resource in order to perform consensus. So how are we going to do that? And so let me first give you a naive proof of stake. So by the way, the amount of coins is called stake. It's kind of the stake you have in the system, right? The more Bitcoin you have, the more stake. So let's write down what we have for proof of work. So this is the problem that I'm trying to solve. The hash of I have the hash of the previous block. I am concatenating right, so this is the sign for this. So I have a nonce and I have a timestamp, and of course I have a Merkle root and so on. The Merkle root is like a summary of all the transactions in the block, and I want this to be less than some sort of threshold. And the threshold can be adjusted by the protocol depending on how fast you want blocks to be generated or how slow. Right? So this is proof of work, and let's look at a naive proof of stake protocol. Right? So I'm trying to create another problem to solve, but it shouldn't require a lot of computation. Right? So of course I need a pointer to the previous block just to have a blockchain. So let's say I put this hash of the previous block into my header, and then what I am going to do, let's say I have a timestamp, I'm going to call it T. And I don't want to have a nonce, because then I'm back to proof of work, right? Because I want to have something like this. And now what I want to put here is some information about a stake that a person has, right? And let's say that I put A, which is my, let's say my some sort of an account number. Or it's some sort of a public key. Right? So suppose I own a certain amount of ether in the system, right, and my account number is A, right. I am going to put that account number here, right. Okay, so I am going to take a hash of this, and I can't replace too many of these things, so this timestamp is limited to a small range. Okay, so this is not like a nonce where I can put anything that I want. Okay. It's just few values. Let's say T is, let's say it's within 1 hour of the current time. Let's say it's time in seconds, and plus or minus 1 hour from the current time. Right, so there's not a whole number of values that I can put there, because everybody knows what the current time is, and I can just put a few thousand values for that timestamp, right? Okay. And let's say I've got one account with a particular account number, and let's say that the problem that I want to solve is this. Okay, so let's say that I start out with this, right? So again we have a blockchain like we had before. This is the current blockchain, and the question is what is going to be the next block. And there are various people who are trying to solve this problem, this naive proof of stake problem, in order to decide what's going to be the next block. Right? So let's say that somebody has an account number and he wants to do this, right? So now there is a slight issue over here. So first of all, is this Sybil resistant? Okay, so let's say that there is account number A, and it, let's say, has a particular balance. So this is the amount of stake which is mapped to that particular account number. It just says that there is this much ether owned by somebody who has account number A. Okay. So suppose I'm the owner of A and I want to have a higher chance of creating a block, and this is the puzzle, this is the problem which I have to solve. What would I do? Okay, so maybe now, of course, I mean, I can just try to solve the problem here, but suppose I divide this balance into 10 accounts. Suppose I split this up, this amount, and I can just pay myself on the blockchain, right? And I can create many accounts, let's say 10 accounts, right? And let's say that each of these has 1/10 of the original amount, right? I've created 10 accounts for myself. Now with each of these accounts I will be able to, oops, what did I do? Okay. So what do I do for the pointer, the middle one? Okay. But I did that. Okay. Anyway, I think I can just use this. So suppose I am malicious, what I could do is I could split my ether into 10 different accounts, and with each of these, whether it is A1, A2 and so on, I could try to solve this puzzle, right? and maybe I'd be the first one to solve this puzzle just because I have more accounts. Right? So this is not really solving the Sybil problem, because people will just create thousands and thousands of accounts for themselves, and then they have a higher chance of solving the problem. Right? So what do we need to do? We need to change this in some way, and somehow this puzzle has to have the balance that a person owns. Okay, to ensure that he cannot perform an attack like this and create lots and lots of accounts. So anybody want to suggest what we should do, where we should put this balance in this formula? Yeah, we should put it this side. So I'm going to put it over here on the right hand side. Okay, and you can show that now it doesn't make sense to actually split your money into many accounts. Okay, the chances of your creating the first block after this is not going to increase in any way if you split your money into many accounts, right? Because even if you, let's say, split your money into 10 different accounts, the right hand side is going to be, let's say, it's going to have balance A over 10. So each, you're going to try to solve 10 puzzles, but each is going to be 10 times harder. So you're not going to gain anything, right? So this is going to solve the Sybil problem. Yeah.
But then the threshold will be different for everybody. The whole.
Yes.
Those who have higher balance would have higher chance of solving the problem.
Yes. So that is okay. So his point is well taken. He says that not everybody is solving the same problem, and whoever has more balance has a higher chance of winning. So this is analogous to the earlier case where if you had more CPUs, you could solve the puzzle faster, like in proof of work. So here this naive proof of stake method is saying that if you have more stake, you have a higher chance of solving the problem, right? But you can't pretend that you have more stake than you have, because everything is available on the blockchain. Everybody knows how much coin is associated with how much, which account, right? So you're right. So the richer people get richer, right? And that's true in any case in real life, right? The big industrialists have a lot of money, they make more investments and they earn even more, right? And even in Satoshi's case, the more CPUs you have, the more blocks you're going to generate and the more Bitcoin that you're going to earn from mining blocks, right? So here the richer, the people with more stake will have a higher chance of solving the problem, but they can't launch a Sybil attack. They cannot pretend that they have more coins than they do. Yes, so there's.
Can we not introduce some kind of social security like Aadhaar?
Some sort of an Aadhaar sort of.
Instead of account number, we put Aadhaar there.
Yes.
Identity, which is physically checked by government.
Yes. So that would bring us to more of a permission system. So we are right now talking about permissionless systems where anybody can join and participate in the consensus. So once you have an Aadhaar-like system, so the comment was that why don't we have an identity system like Aadhaar, right? And that would make it a permissioned system where we have some sort of a centralized authority which is saying what is your Aadhaar and ensuring that you cannot fake it, right? Yes. So the government used Aadhaar to solve a Sybil sort of attack, right? So people were using that, creating multiple identities to do some sort of mischief, right? And Aadhaar solves the problem for the government, right? But in a permissionless system, how do we do it? Because there are no such identities.